This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss the scoring guidelines for the 2022 AP Calculus exam, free response question BC2. My name is Steve Kokoska. I'm a professor emeritus at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here is an outline of the information presented in this video. I'll start by reviewing the free response question, the point distribution, and then the scoring guidelines used at the AP Calculus reading in Kansas City and for readers off-site. I will present more detailed solutions where appropriate, and then I'll consider a more thorough interpretation of the scoring notes and how these notes were applied in certain situations. I'll consider some common student errors where it is relevant. And finally, I'll include a few extra problems for you to consider, all associated with this question. The format for the AP Calculus scoring guidelines has changed in the last few years. So, just a few general notes before we begin. The model solution presented in these guidelines is given using standard mathematical notation. In general, other solutions presented using correct mathematics are eligible for all points. And remember that a final numerical answer does not need to be simplified. If a response includes an error in simplification, then the response will most likely lose a point. Decimal approximation answers must be given to 3 digits to the right of the decimal, rounded or truncated. And within each question, at most 1 point is lost for inappropriate rounding. This question is calculator active, and it involved the particle moving in the xy plane. Its position is given by the coordinates x of t, y of t for t greater than 0. We are also given expressions for dx dt and dy dt, and we know the position of the particle at time t equal 4. In part A, we need to find the slope of the line tangent to the path of the particle at time t equal 4. And part A was worth just 1 point. 1 point for the answer with supporting work. Here is just a little bit more detailed solution and a calculator illustration. As is often the case with particle motion problems, we need to translate the question into mathematics and simply use or apply the correct formula. Here, the slope of the tangent line at t equal 4 is dy dx evaluated at t equal 4. This is, by definition, y prime of 4 divided by x prime of 4. And since the expressions for x prime of t and y prime of t are uncomplicated here, we can find the symbolic answer by hand, that is, without a calculator. It's log of 18 divided by the square root of 17. And the decimal equivalent is 0.701. I'm going to use the TI-Nspire CAS calculator to obtain the technology solution. So first, I defined the functions xp for x prime and yp for y prime. Then I found the slope of the tangent line at t equal 4. Now, notice that the calculator returned the symbolic answer rationalized, and this would certainly be accepted on the exam. But here, I converted the answer to a decimal. The slope of the tangent line at t equal 4 is 0.701. Here are the scoring notes associated with Part A. To earn the point in Part A, the response must present the mathematical setup used to obtain the slope of the tangent line. Here are 3 minimal examples that earn the first point. Note that just a plain response of 0.701 does not earn this point. There is insufficient mathematical evidence of the setup used to obtain this decimal answer. A response that equated a function to a constant did not earn this point. Now, this seemed to be a common issue throughout the exam this year, and I'm not sure why. This means that the response cannot write an equation in t and equate this to a constant, even if it is the correct constant. This will not earn the point. However, the response will not lose any additional points in this problem for a similar error. Here are some of the common errors observed in Part A. Now, most students recognize the need to work with the quotient dy dt divided by dx dt and to evaluate this expression at t equal 4. However, there were some common communication errors. Specifically, many responses equated a function in t to a specific constant, the function evaluated at t equal 4. And some students presented the reciprocal of the correct answer. In Part B, we need to find the speed of the particle at time t equal 4. And we need to find the acceleration vector of the particle at time t equal 4. Part B was worth 3 points. The first point was for the correct speed, with of course supporting work. And the second and third points were for the acceleration vector components. Again, we need to translate the question into mathematics and use the correct formula. The speed in the particle at time t equal 4 is given by this expression. We can actually find this answer symbolically, but the decimal equivalent is 5.035. And the acceleration vector is given by this expression. These two components can also be found symbolically. But since this is a calculator active question, it's probably better to use technology to find the decimal answers. Here is how I used the calculator to obtain the answers. I entered the expression for the speed of the particle at time t equal 4. Note that this CAS calculator returns a different looking but correct and acceptable answer. But here's the decimal answer. And to find the acceleration vector, well, I found each component. Here's the x component, symbolically, and the decimal equivalent. And here's the y component, symbolically, and the decimal equivalent. Remember that the student needs to report final decimal answers with 3 digits to the right of the decimal, rounded or truncated. Here are the scoring notes for Part B. Now, once again, to earn any of these points, the response must present evidence of the mathematical setup used to obtain the correct value. Bluntly, there must be supporting work. There are a couple of examples in the first item, and there is a special case associated with the acceleration vector given below. The second and the third points can be earned independently. That is, one component can be correct and the other incorrect, and that would earn one of the last 2 points. And here's another reminder that good communication skills and notational fluency are expected. If the acceleration vector is not presented as an ordered pair, then the components must be labeled. Readers cannot be expected to decide which value is the x component and which is the y component. Unfortunately, if the response presents the acceleration vector with the components reversed, then the response does not earn either of the last 2 points. And here's an example. This is a little unfortunate, but the response is incorrect, and it has miscommunicated a basic concept. Some students actually found x double prime of t and y double prime of t symbolically, either by hand or using a CAS calculator, and they reported these functions. If the response did not evaluate these expressions at t equal 4, then it still earns one of the last 2 points. And finally, a succinct response like this earns one of the last 2 points. Now agreed, there isn't enough evidence of a mathematical setup, but we're pretty sure we know where these values came from. Here are some of the common errors that we observed in Part B. First, students in general knew the correct formula for the speed of a particle at time t. However, many students equated the speed function with the value of the function at t equal 4. Some responses used the absolute value of v without defining or presenting an expression for v. Therefore, this was considered insufficient evidence of a mathematical setup to compute the speed of the particle. There were several parentheses errors, and this resulted in ambiguous or incorrect expressions. Many responses attempted to find the components of the acceleration vector symbolically, and this was certainly possible. But for those who attempted this, many made either a chain rule error or a power rule error. Some responses actually tried to find the length of the acceleration vector rather than just the vector itself. And some responses used incorrect labels or no labels on the vector components. And you can certainly see the value of good communication here. In part C, we need to find the y-coordinate of the particle's position at time t equals 6. And part C was worth 3 points. The first point was for the correct integrand, log of 2 plus t squared. The second point was for using the expression y of 4 in finding the y-coordinate. And the third point was for the final answer. Here is a little bit more detailed solution and how I used technology to find the answer. We are given the y-coordinate of the particle's position at time t equals 4, and we need to find the y-coordinate at time t equals 6. Now, I see this as a problem that involves the fundamental theorem of calculus. And here's the basic expression involving the given information. The definite integral from 4 to 6 of y prime of t dt is equal to y of 6 minus y of 4. Solve this equation for y of 6. And now we can interpret this equation as the y-coordinate of the particle's position at time t equals 6 is equal to the y-coordinate of its position at time t equals 4 plus its change in position in the y direction from 4 to 6. Now I'll use technology to evaluate the definite integral, and finally find the y-coordinate at time t equals 6 is equal to 11.571. Using the TI-Nspire, I evaluate the definite integral. Note that I could get a symbolic answer for this. And then I simply added 5, or y of 4, to this value. And here is the 11.571. Here are the scoring notes for part C. In this part of the problem, the first point is earned if we see the function log of 2 plus t squared in either an indefinite integral or an incorrect definite integral. Look, the idea is we need to see the correct integrand in the context of an integral. If the definite integral presented has incorrect limits, then the response is not eligible for the answer point, and this makes sense. If the limits are wrong, then the answer cannot be correct. And similarly, if an indefinite integral is presented, the response is not eligible for the answer point. If there aren't any bounds on the integral, well, then there really can't be a final answer. I interpret this next item as really two separate thoughts. First, to earn the second point, there must be evidence that the response has added the value for y of 4 to a definite integral. And if the response instead finds the x-coordinate of the particle's position at time t equals 6 all correct, then the response earns 2 out of the 3 points in this part. If the response does not use y of 4, then it can still earn 2 points. And here's an example. Y prime of t is used in an integral with correct limits, and the evaluation is correct. So this would be scored as a 1, 0, 1. And finally, we have a few scoring rubrics here for the case of the missing differential. In the first case, we assume that the dt is at the end of the expression. So this response earns the first point, and it could earn the third for a correct evaluation of the definite integral. There is no use of y of 4 here, so the second point is not earned. In case 2, the integrand is ambiguous because of the missing dt. So the first point is not earned. But if the response presents the correct answer, then we would award the second and third points. And in case 3, this expression earns the first 2 points. It is eligible for the third and would earn it with a correct answer. Here are some of the common errors observed in Part C. Many responses presented an indefinite integral, and several simply did not incorporate the initial position y of 4 into their answer. Although this was a calculator active question, several students attempted to determine the integral of the log of 2 plus t squared dt using integration by parts. Now, an antiderivative can be found using this method, but few students who tried this were successful. And some students, using a CAS calculator, worked with the symbolic answer for the definite integral. One representation is shown here on the TI-Nspire. This was unnecessary in this problem, and unfortunately, it usually led to presentation errors. In Part D, we need to find the total distance the particle travels along the curve from time t = 4 to time t = 6. Part D was worth 2 points. The first point was for the correct integrand, and the second point was for the correct answer. Here's just a little more detailed solution. The distance the particle travels from t = 4 to t = 6 is given by this definite integral. And then I just need to evaluate this expression. On the TI-Nspire, I evaluated the definite integral to obtain 12.136. And again, what I needed to do to solve this problem is to translate the question into the mathematics, use the correct formula, and evaluate as necessary on the calculator. Part D was pretty straightforward, and therefore there were only a few scoring notes. The first point is earned for presenting the correct integrand in a definite integral, so we need to see something like this, with limits. To earn the second point, the response must have earned the first point. They must have presented the correct integrand in a definite integral, and they must present the correct value, 12.136. And finally, just a 12.136 on the page does not earn any points in this part. Now, I understand that many students are very good at these problems, and they can read them and go directly to their calculator to get the answer. But we require the correct mathematical setup used before evaluating the expression with technology. Here are a few of the common errors observed in Part D. Now, it seems that most students understood the concept here, but many simply did not present the mathematical setup properly. Missing parentheses and misplaced 2's in the exponent were common. Several students appeared to treat this question as a one-dimensional arc length problem, and they presented and evaluated this definite integral. Well, this earned 0 points in Part D. And it was also common to see this incorrect definite integral. This also earned 0 points in Part D. Here are a few additional questions to consider that use the information presented in this problem. I won't read through all of these, but I think there are some good, interesting problems here, and most that require the use of technology. During the actual AP Calculus reading, readers review the scoring guidelines, discuss this document with a table leader, and learn more about scoring the problem by working through training feedback samples. I hope this summary video captures the important aspects of this process and gives you a good idea of how this question was scored. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.